So the first one here says, suppose an experimental population of fruit flies increases according to the law of exponential growth. There were 100 flies after the second day and 300 flies after the fourth day. Approximately how many flies were in the original population? So we're going backwards here. Okay, that's our goal.
Could you kind of assume that it's like 0 flies or
Well, if you had 0 the first day, you wouldn't have any on the fourth day either.
each day.
What?
It increases by 100 each day.
Well, if it were linear growth, then yes. But here we're growing by exponential growth.
There's gotta be at
Okay.
least 2 flies.
Huh?
There's gotta be at least 2.
Gotta be at least 2, alright? So, biology tells us there's gotta be at least 2 flies. So, let's go on and let's figure this out. What's our exponential model?
CE to the KT.
Alright, y equals CE to the KT. And we're actually looking for C here, right? So we're given 2 different counts, so one on day 2, one on day 4. That's 2 points, right? So we have the point 2, 100 and 4, 300. Okay? So you can use this model to get 2 equations with 2 variables. We don't know what K is, we don't know what C is, but we do know that it equals 100 when we have CE to the 2K, and we know it equals 300 when we have CE to the 4K. And then again, remember this is similar to back when you were doing geometric sequences back in pre-calculus. Alright, you can set up a proportion to solve these. And we have e to the 4k over e to the 2k. Well, the c's were there too, but they cancel. And that's going to equal 300 over 100. Okay? So that means e to the 2k equals 3. So what does k equal? Yeah, ln of 3 all divided by 2. Or if you want, you could do ln of radical 3. That's your k. Now we can back substitute. Okay? And if I do it into this one here, I have 100 equals c times e to the 2 times ln of 3 over 2 power. Okay, so the 2's will cancel. E to the ln of 3 equals 3. So we have 3c equals 100. So c is going to be 33 1/3, right?
How do you go about that?
Well,
Would you just say 33?
I would approximate 33 flies.
Okay.
Not fleas, flies. Hopefully we don't have 33 fleas. Okay? Yes?
So since we got e to the power of 2k is equal to 3, can we just say that 3c is equal to 100?
Oh yeah, you could have. Yeah, since our main goal wasn't to get the model, our main goal was to figure out C. Yeah, that's really good thinking, Gloria. When we get to this point right here, we could go ahead and plug that in right there. And that would take us all the way down to, not that step, that would take us all the way down to that step a lot faster. Yeah, it's great thinking.
Okay.
That's great thinking. Okay? Alright, and you can see here the model that we've got. Notice they approximate it to be 33 as well. Okay. Alright, let's try another one. Here we have declining sales. Alright, what's the impact of not doing any advertising on our business? Okay, so we have this manufacturing company. 4 months after it stops advertising, it notices that its sales have dropped from 100,000 units a month to 80,000 units a month. If the sales followed an exponential pattern of decline, what will they be after another 2 months?
So C equal 100,000.
Yeah, here they gave us what C was. It was 100,000. So now we know that Y is 100,000 e to the kt. And we have 1 point given to us. After 4 months, it equals 80,000. So 80,000 equals 100,000 e to the 4k. So you have 0.8 equals e to the 4k. ln of 0.8 divided by 4 is the k. Alright? So now y is 100,000 e to the t times ln of 0.8 over 4 power. And then, well, what do we plug in? 6. Another 2 months means that t equals 6. Yeah, be careful with that one. Okay?
Had you not realized that that 100,000 was like your C, could you have done it the same way we did it before by saying 0, 100,000, and
Yeah.
and it still would have came?
Yeah, it still would have worked out. Because the one equation would have been, okay, equals 100,000 when C e to the 0k,
Oh,
and then e to the 0k is 1, so C equals 100,000. Okay? Alright, do we know what this equals then if we plug in 6? Okay. Y of 6 is...
I got 71,554.175.
Okay, so we'll go approximately 71,554 will be our sales. Does that make sense? Yeah, that's a reasonable answer. It's lower than 80,000 at least. Okay? Alright. So we have those two. Let's try one more. This is kind of an interesting one here. Dealing with Newton's law of cooling. Any of you ever studied this at all in science class or anything?
Newton does a lot.
Huh?
Newton does a lot.
He's done a lot. He was pretty significant character in our scientific history, and mathematical history. He was one of the inventors of calculus, so Newton and Leibniz. So Newton's law of cooling basically is telling us how, if you have something that is a temperature other than the temperature in the atmosphere, it's a way to measure like how it's going to change temperature to reach a state of equilibrium. Eventually, if I have a hot cup of coffee, I set it on the table and the room is, 78 degrees. Eventually, if I let the coffee sit there long enough, the coffee will be 78 degrees. Okay, if everything else stays the same. Newton's law of cooling would help me model the temperature change as it goes. In fact, one of the HL math students did their IA on Newton's law of cooling to figure out how long after his tea boils he should drink it if he likes to drink it at a particular temperature. So it's kind of an interesting study there that he did. But anyways, it says here, Y is the temperature in degrees Fahrenheit of an object in a room whose temperature is kept at a constant 60 degrees. Okay, so the room is 60 degrees. If an object cools from 100 to 90 degrees in 10 minutes, how much longer will it take for its temperature to decrease to 80 degrees? Okay, so let's look at the Newton's law of cooling. It says that the rate of change in the temperature, so I'm going to use a capital T for temperature. So the rate of change in temperature over time is proportional to the difference, so K times a difference here, the difference between the object's temperature and the temperature of the surrounding medium, okay, or you could say the temperature of the room. So it's the difference between those. So I'm going to do T sub 0, or T sub O for the temperature of the object, minus the temperature of the room, T sub R. Okay? So this is Newton's law of cooling, the rate of change. Now, using our exponential growth or decay function here, we could separate variables. Alright, so I'm going to have 1 over T sub O minus T sub R. Okay. And then I'm going to have a K dt on this side. Alright. So actually I should have put this down here. Okay. So K dt equals 1 over T sub 0 minus T sub R dt. Okay? Now, one thing here is that the room is staying a constant 60 degrees. So T sub R is a constant. Before I go any further, I'm going to plug that in. Okay? The temperature of the object is what is changing. Okay? So that's what I really want. So I'm actually going to, I don't even need to put the O there anymore. Okay? That's the temperature of the object. But now what I can do is I can integrate both sides. And I have K times the time plus some constant equals ln absolute value of t minus 60.
So that would be
Okay?
C e to the KT.
Would you plug 80 in for T, like lowercase t?
Eventually we will. Eventually we will. What I'm doing is I'm kind of re-deriving what we had done here. I'm going to put E as the base on both sides. And I'll call that a C1 for now. But notice what I'm going to have is the absolute value of t minus 60 equals e to the kt times e to the c1, so some constant. Now that constant is the starting amount, but understand here that the starting amount, because I have this t minus 60 over here, we're talking about differences in temperature. So this is the starting difference in temperature. Which in this case is going to be from 100 to 60, so 40. All right, so coming over here, we have t minus 60, which I'm actually going to ignore the absolute value at this point because our temperature is decreasing, so I know t minus 60 will always be positive. And that's going to equal 40 the starting difference in temperature times e to the kt. And now here is where we can use this other bit of information. It said it went from 100 to 90 in 10 minutes. So they just gave us a point. The temperature is 90 when t equals 10. So 40 e to the k times 10. So now 90 minus 60 is 30, divided by 40. I have a 0.75 equals e to the 10k. I take the ln of both sides and divide by 10, and I now have k equals 0.75 ln of 0.75 over 10. So that is my constant. Now, the point of the problem was to find out how much longer will it take for this temperature to decrease to 80 degrees, okay? So if I'm going to 80 degrees, that means I'm going to now plug in 80 minus 60 equals 40 e to the, I don't know what t is, that's what I'm looking for, ln of 0.75 over 10. So now I have 20 over 40, which is 0.5, equals e to all of that. I take the ln of both sides. That equals t times ln of 0.75 over 10. And now I get t equal to 10 ln of 0.5 over ln of 0.75. And that time is 24.094. Now the problem asked how much longer will it take. So if I subtract the original 10 minutes, that means my final answer would be 14.094 minutes longer. And notice it only took 10 minutes to drop 10 degrees at first. Now it's taken 14 minutes to drop 10 degrees. And that's because this is exponential, it levels off, and the closer your temperature gets to the temperature in the room, the slower that temperature is going to decrease. It's going to slow down and level off.